Hello, everyone. Everyone's doing well. Gonna wait maybe 1 or 2 more minutes for the rest of people to join in. Ooh. Good morning. We'll wait 1 more minute. Hope you guys had a nice vacation. I was telling my other classes that I always know I've had a good vacation when I um, I can barely remember my work passwords when I get back, and I had to think about it. I couldn't remember my work password, so that means that I really relaxed. If you sent me a message, uh, I think I got a lot of messages on Friday, and I was already checked out. So I apologize if you sent me a message and I didn't respond. Okay, so I'm gonna go ahead. I'm gonna go ahead and get started. I want to remind you that today's class ends at 10:15. So this class goes from 9:45 to 10:15. I'm typing that into the chat. Um, period 5 starts at 10:20. Um, so I just typed that into the chat. Also, I want to remind you to submit attendance. There's going to be no Zoom room today, so I have no clue who's watching and who is not watching. So submit attendance to the Zoom or to our via our Google form, because there's no Zoom room today because of the shortened class period. I also wanted to say that I don't think that we will completely get through our content for today. All right. So today's lesson, the quiz, you don't know how to do the quiz yet, so don't start the quiz today. So that's all I have to say about that. So let's go ahead and get started. So today we're going to talk about something called angular momentum. Okay, which is denoted by a capital L. Okay, and angular momentum somehow quantifies the amount of spinning. Okay, it quantifies the amount of spinning. All right. So there's a formula for angular momentum. And so what I want to consider is an object of mass m that is moving in a circle. Okay, so we have an object of mass m that's moving in a circle. It has a speed v, and the circle has a radius r. Okay, and for this object, so we can think about this like for example, a planet orbiting the sun, or we could think about it like a tether ball or something like that. The angular momentum is equal to the mass times the velocity times the radius of the circle. Okay, so this is the formula for angular momentum, for the amount of spinning. Okay, so you can see more spinning means you're going faster or you're going in a bigger circle. Okay, so that is angular momentum. All right, and so based on this definition of angular momentum, okay, the units of angular momentum are something we can calculate. Okay, and so units of mass are kilograms. Units of velocity are meters per second. And units of radius, well, radius is a distance, so that's another meter. So I'm going to put meters squared. So the units of angular momentum are kilogram meters squared per second. Okay? So now I would like to answer the question, well, why is angular momentum useful? Why would we even bother to calculate angular momentum? Well, it turns out that if a system has no torque acting on it, then that means that angular momentum will be conserved. Okay? So angular momentum is conserved, just like linear momentum and just like energy. Okay? So it's another quantity that nature conserves. Okay? And so that is why it is a useful thing to talk about. Important point, this is only going to be conserved if there is no torque acting on the system. So remember, when something is conserved, it means that its value is not changing. So it means that L is a constant. That being said, of course, the things that make up that value, like velocity, can change, speed can change, but only if the other quantities change in a way that compensates for that. Okay? So angular momentum is constant, or we could think about it as the initial angular momentum is equal to the final angular momentum. Okay? So let's do an example of using angular momentum conservation. Okay? And that example that I think of oftentimes is tetherball. Do they still play tetherball? I don't know. Is that even a playground game anymore? So let's imagine a game of tetherball. And so let's imagine it from a side view. All right, a side view of a tetherball game. So here's the tetherball pole, and here's the rope, and here's the tetherball, and it's going around like this. Okay, so it's going around in its circle. Okay, so let's suppose at this instant the speed of the tetherball is let's say 3 meters per second. And furthermore, let's suppose that the radius of this circle that the tetherball is moving in is, let's say, 2 meters. Now, what does the tetherball do? It winds around the pole, okay? So here's the pole. The pole is the same. But as the tetherball goes around the circle, it winds around the pole like that. And as a result of that, the string gets shorter. And now it's moving in a smaller circle. Okay? This smaller circle only has a radius of 0.35 meters. Okay? So the question is, what is the speed of the tetherball in the end? All right? What is the speed of the tetherball in the end? So the rope can't exert any torque on the tetherball. Why is that? It's because the rope is parallel. It's pulling parallel to R. So remember, the formula for torque is F per R. So in a tetherball game, we have no torque, since the perpendicular component of the tension from this rope is equal to 0. And so consequently, angular momentum is conserved. All right? So I write my angular momentum conservation equation. So I have mvr equals mvr, where on the left-hand side I have initial values, and on the right-hand side I have final values. Now the mass of the tetherball is not changing as it gets wound around the pole, okay? And furthermore, I can see that mass is on both sides of this equation. Okay, so that means that m cancels out. So that is why I did not need to give you the mass of the tetherball. I only had to tell you, the speed and the radius of the tetherball. So the initial speed of the tetherball is 3 meters per second. The initial radius is 2 meters. The final speed is unknown, so I leave that as a variable. The final radius is 0.35. I can take this and solve for the final speed. And I get that the final speed is 17.1 meters per second. All right. So I was looking for something to demonstrate this phenomenon. Oh, I have an HDMI cable. Okay. So basically, what this is saying is as the thing winds up, it goes faster. So things go faster as they wind up. Okay, so you have probably noticed this before. Okay, so if I take this, HDMI cable and I spin it around in a circle, and then all of a sudden I let it wind around my finger, it will actually. So this is actually a bad example because the HDMI cable is so thick that when it gets spun in a circle, air resistance is a significant force. And so air resistance actually exerts a torque, which slows it down. But if you had something that was not like an HDMI cable, then as it winds up, it would actually speed up. Okay? So you've probably observed this before. I'll find a better example for period 6. Okay. One of the things I want to say about angular momentum, okay, is that if the sense of rotation reverses, then L changes sign. Just like torque, just like angular velocity. Turn the slide out so it's a little bit. So if something is spinning in the counterclockwise sense, that is a positive angular momentum. And if it is rotating in the clockwise sense, that is a negative angular momentum. So, all right. So I want to talk about something that I think is really fascinating. Okay. So let's talk about the solar system. All right. Here's the sun. Okay. Here's Mercury, Venus, Earth, Mars. Now these are not accurate relative distances. Jupiter, Saturn, Uranus, and Neptune. Okay. Here's something that is really cool about our solar system. If we look at all the planets, all these planets are moving in circles around the sun, or approximately circles around the sun. Okay? Did you know that all of these planets are going around the sun in the same sense? They are all going counterclockwise around the sun. Did you guys know that? Okay, so they all have positive angular momentum. This is called orbital angular momentum because it's an angular momentum associated with the orbit of the planet. Okay. Furthermore, we also have what's called spin angular momentum, which is because the thing is spinning. Okay. Because the thing is spinning like that, the Earth is rotating about its axis. It has spin angular momentum. Now, if we look at all the planets are orbiting counterclockwise, but all the planets are also spinning about their axes counterclockwise. So they're all spinning counterclockwise. With the exception of one planet, which is Venus, which is spinning the opposite direction, and I'll talk about that in a second. So Venus has a so-called retrograde rotation. Okay, the sun itself is spinning, and it's also spinning counterclockwise. All right. Furthermore, if we look at all the moons, so for example, Mars has 2 moons named Deimos and Phobos. Those moons are also going around counterclockwise. The Earth's moon is going around counterclockwise. Okay? Jupiter's moons are mostly going around counterclockwise. Saturn's moons are going around counterclockwise. Okay? So, the lesson is that with the exception of a few things, with the exception of a few things, everything in the solar system has positive angular momentum. It's rotating counterclockwise. Okay. Now, why is this? Well, we believe that the solar system formed from a single cloud of gas, and that cloud of gas had positive angular momentum. And then that cloud of gas started to condense due to its own gravitation, and as it condensed, we had basically planets and stars condensed out of that cloud, and so as a result, they were all spinning counterclockwise. So basically, the fact that everything has positive angular momentum is evidence for the fact that everything came from the same origin. Okay? That's one piece of evidence. And then we could also look at compositions and things like that to determine, to further deduce that. Okay? So I think that's really neat. You might not have realized that, but everything is going counterclockwise, with the exception of a few things. So things like Venus, we believe that when Venus was formed, it was originally spinning counterclockwise, but then it got hit by something. So early in the solar system, it was a lot more common for large astronomical bodies to smack into each other in the early solar system because it was so much more filled with stuff in the beginning. And so we believe that one of those collisions probably was so huge that it actually reversed the spin. So things like that can cause the angular momentum to flip if two bodies are interacting and they smack into each other. So I think that's really neat. And so if we look at the Great Conjunction, for example, one of the things you could see is that the planets, the Great Conjunction was the fact that Jupiter and Saturn were really close to each other in the sky. They're both orbiting in the same direction, but because Jupiter is closer to the sun than Saturn, it's orbiting faster. And so we can see that Jupiter will eventually get ahead of Saturn. Okay, and that's why they started to separate. All right. So the orbital angular momentum, is given by mvr. Okay, but there is also this fact that as the thing is orbiting, it could be spinning. So we also have the concept of spin angular momentum, and the formula is different. The formula for spin angular momentum is the inertia of the spinning body times its angular velocity. And this is the angular velocity of the spinning about its axis. Okay? And so the total angular momentum is going to be the spin or angular momentum plus the orbital angular momentum. Okay? So you can actually have a transfer of angular momentum from spin to orbital, for example. And this actually affects, so like what would happen if you had angular momentum go from spin to orbital? An object will start spinning more slowly, but its the radius of its orbit will get bigger so that its orbital angular momentum increases. So you can have these so-called spin-orbit interactions where the total angular momentum stays the same, but it transfers from spinning to orbiting or vice versa. One of the things I want to point out is the analogy between linear and angular quantities. So if we think about linear momentum, okay, linear momentum is given by the formula m times v. All right, MVP, most valuable physicist. Angular momentum, at least spin angular momentum, is analogous to linear momentum. Because what is analogous to mass if we're talking about things that are spinning? It is inertia. What is analogous to linear velocity if we're talking about rotations? Angular velocity. So you can remember the formula for spin angular momentum if you remember the analogy between linear motion and rotational motion. Okay. So we're going to talk more about this tomorrow, Thursday. And so don't start the quiz yet because there's more to learn here. I can't remember if I said this or not, but the fact that Venus is spinning in the reverse sense, that's called retrograde rotation. So if it's spinning the correct way, it's called prograde rotation. So prograde versus retrograde is another vocabulary term. The other thing I wanted to talk about is just in the last couple minutes is, did you know why do we always see the same face of the moon? It's because the orbital period of the moon is exactly the same as the period of its spin. So it's kind of like this. The moon is going around. Okay, if the moon was not spinning, it would go around like this. But the moon is spinning, and so it's spinning at the exact rate such that it's always the same part is facing the central body. Always the same part is facing the Earth. Okay? This is actually a general phenomenon. It's called tidal locking. You can look it up. So we would say that the moon is tidally locked to the Earth, and basically all moons in the solar system are tidally locked to their planets. Okay, so you might not have known that. Have a good day, and I will see you on Thursday.